Hello, this time we're going to consider that case of polynomial division and function evaluation. And for that, we're going to take an example. And in this case, we have a function that is given by a polynomial of degree 3, just like this one, x cubed minus 6x squared plus 8. And we're going to evaluate it at a particular value, in this case, x equal to 2. After some computation, it turns out that the value of this function at 2 is negative 8. Up to this point, well, really not too much new nothing new under the sun. But how can we connect this process with polynomial division itself, right? Well, let's start by the division algorithm. Right? We have the following. There are unique polynomials q of x, the quotient, and r of x, the remainder, such that we have f of x is expressible as x minus 2 times q of x plus r of x, right? Where the degree of the remainder is strictly less than the degree of the polynomial x minus 2, which clearly is 1. So what is this saying? Then r of x is a number. And what number is it? Well, let's find it out, right? And to that we're going to explore, well, first, the method of long division. So we're going to perform every single calculation, and I hope that you, well, if you don't mind, you can accelerate the video, or you can watch it in detail just to be clear on how to process this step by step. So we'll do it. We have x minus 2, right, as the polynomial that we use to divide, and x cubed minus 6x squared plus 8 as the one that we're going to use to divide, to be divided. Now, how do we start the process? Well, on every single iteration of this, we have to get rid of the element, the term of the highest degree in the dividend. So, to that extent, what I'm going to use is, well, I wonder, how can I get rid of this x cubed with this x, right? Well, to do that, I'll start like this. Well, look, there's a hidden coefficient here of 1, and there's a hidden coefficient here of 1. So that tells me that I need 1 times and then something about x. Well, how much? An x squared. So when I multiply, I get the following expression. Minus, as in the regular division, minus x cubed minus 2x squared. Of course, from here, we get the following. We have negative 4x squared, I'm just subtracting, plus 8, and then I restart the process. Look, the coefficient that I have here, and this one, indicates me how much I need. So I need negative 4. But negative 4 of what? Well, I need to cancel this x squared with this x, so I need an x for that one, right? So I'll continue with the multiplication. So now this term against all of this. So let's do it. This is negative of negative 4x squared plus 8x. From here, we obtain that this reduces to negative 8x plus 8. And once again, this coefficient tells me, along with this one, how much of x I need, right? How much do I need to put here in the quotient? So that would be, well, minus 8. But how much? Well, this time I don't need an x, because when I multiply this negative 8 by x, I will be able to cancel this portion. So I'll do it. So I have minus negative 8x plus 16. And from here, we see that what remains is negative 8. Okay, let's put it in a summary, right? All of this calculation summarizes to the following equation. We can say x cubed minus 6x squared plus 8 is expressible as x minus 2 times x squared minus 4x minus 8 plus negative 8. Because what we're doing here is we multiply this quotient times this, and adding this portion should gives us back this original polynomial. Okay, but now note that when we perform the evaluation at 2, we already know what the value is supposed to be. But now we have further justification. Because look, all that happens is that I make a replacement not on this original expression, but on the one that we obtained from the polynomial division. So now we have 2 minus 2 times 2 squared minus 4 times 2 minus 8 plus negative 8. Of course, we don't even have to worry about this value. Who cares what it is? Why? Because we know what this is. This is 0. So 0 against anything is just 0. So that saves us a lot of computations. And this indicates that this has to be simply negative 8. Okay, so we can say the value of f at 2 is the remainder of the division of f of x considered as a polynomial by x minus 2. Of course, this result may be extended to any value of 2, or any value of x other than 2, right? There's really nothing that prevents us from doing that. Okay, now the question now is there a faster way to calculate both the quotient and the remainder? Well, let's see. Okay. We start with the following observation. I'm going to examine this equation that we have here, right, that I'm just underlying, and I'm going to transport it here. So I have x cubed minus 6x squared plus 8 equals to the following: x minus 2 times x squared minus 4x minus 8 plus negative 8, just to keep it in that fashion. Now, instead of organizing all of this information in a single line, I'm going to organize it in multiple lines. So I'm going to write the following. So I have x cubed minus 6x squared plus 8 is equal to x cubed minus 4x squared minus 8x on this side. And then the next part is going to be negative 2x squared plus 8x plus 16. The second line being the product of negative 2 against the quotient. And lastly, a negative 8. I mean, it's just another way of writing the same expression, right? Really nothing new. But you may say, well, let's do the following. Let's make an extension out of this. And now let's introduce the following. I'm going to write, instead of writing all of this, I'm going to signify the coefficients. And I'm going to have 1 times x cubed minus 6x squared plus 0 times x. I mean, it's hidden, but it's there, plus 8. And that would be equal to 1 times x cubed minus 4x squared minus 8x, then minus 2x squared plus 8x plus 16 minus 8. Now look, this time I'm going to work out with this equation and I'm going to transport all of this over this side. And I'm going to notice a few things in the process, but just bear with me a couple of seconds. We have 1 times x cubed minus 6 times x squared plus 0 times x plus 8. Well, then I have plus 2x squared minus 8x minus 16, and all of this is equal to 1 times x cubed minus 4 times x squared minus 8x minus 8, right? But now look at what we have here. This is the remainder. This expression that we have here is x times the quotient. The expression that we have here is 2 times the quotient. So being 2, the number that we're interested in evaluating. So look, this suggests the following method. I can incorporate a 0 times x cubed right here, and all that I need to do is to keep track of the computations. So when I add these two together, I get 1. When I add these two together, I get negative 4. When I add these two together, I get negative 8. When I add these two together, I get negative 8 as well. So let's put all of that into a rectangular array. And I'm going to indicate 2, then 1, negative 6, 0, 8. What I have here is that I have kind of like a phantom here, a 0, right? And below that 0, I get a 1 by adding these two. Then I multiply, right, against this 1 to obtain a 2 here. Well, then I'm going to add this 2 and I get negative 4. And I repeat the process. Now I multiply against 2, the 4, right? Then it passes over here to become negative 8. Okay. Now I add this 2, just as I'm indicating here, and I get, well, negative 8. Finally, I take this 2, multiply it against the negative 8, I get negative 16, I add, and I get negative 8. That means that here I can recover the quotient. And here I can obtain the remainder. What does this mean? That we can extend this method for other polynomial divisions. So let me try with something else. Let's say the following. Something along these lines. X cubed plus 3x squared plus 3x plus 1, which we can verify that this is equal to x plus 1 times x squared plus 2x plus 1 plus 0. Okay, now look. This would be as if we were attempting to evaluate the function, right? Not at 1, but at -1, as x minus -1 times x squared plus 2x plus 1 plus 0. Now, I'm going to repeat the process, the one that I just did. And here I indicate a -1. Then I collect the coefficients. So that would be 1, in decreasing order of degree. 1, 3, 3, 1. Then I introduce this phantom 0. And I start my process. I add these 2. I get 1. I take this number, multiply it against this one, and then just place it here. Well, that's a -1. Then I add these 2, I get 2. Take this one, multiply them together, place it here, that would be -2. Add these 2 together, so now you have 1, multiply these 2, place them here, and now we have, well, -1, add these 2, 0. Here we can recover the quotient, here we obtain the remainder. In fact, we can use this method to verify whether a number is a root of a given polynomial. To check if a number is a root. So how so? Well, here's an example. Say that you have this function, f of x equal to x cubed minus x squared minus x minus 2. And well, you wonder if is 2 a root of f of x? In other words, if I evaluate f at 2, do I get 0 back? Well, who knows? But we can use this method. I indicated 2. I indicate the coefficients starting from the largest degree term. So 1, -1, -1, -2. Introduce my phantom 0 here. Add them, get a 1, and then we start this process. Right? Multiply these 2, place it here, 2. Add. Now we get, well, we get 1. Multiply these 2, place it here, you get 2. Combine these 2, you get 1. Multiply these 2, place it here, you get 2. Add these 2, 0. So indeed, from here, we can recover the coefficient, and we obtain the remainder. So we have x cubed minus x squared minus x minus 2 is equal to x minus 2 times, well, This one is degree 0, degree 1, degree 2, remainder. So we would have 1 times x squared plus 1 times x plus 1 plus 0. So indeed, when you evaluate the function at 2, the result is 0. So 2 is a root of f of x. I hope that you like it. Take care and subscribe.